Can y'all hear me okay? Is this volume okay? All right, perfect. So yeah, by the way, the person that asked that question, so Ali wrote a whole book about jitter. So maybe you'll need a little bit more than a couple minutes to answer the question of what is jitter. Okay. Thank you all so much for attending my talk today. I'm Miguel Gandara. I'm from MediaTek. Our team is based out in Irvine, California, and I'm going to talk today about the basics of wireline receiver circuits. Okay, so as I mentioned, I'm Miguel. I graduated BS, MS, PhD. All from University of Texas. So when they say bleed orange, they're talking about me, okay? I was there for a long time. From 2011 to 2016, I was with Intel. At that time, I was actually more doing digital design, focusing on the verification of the high-speed I/O, like for USB, camera controllers, but actually like the controller level, so the digital level and not the analog level. Around 2018, I decided, I wanted to change domains. So I went from digital to the analog mixed signal domain, and that's kind of where I'm working at now. My main focus is DSP-based high-speed wireline transceivers, and my specific focus is actually mostly on the receiver data path, which is where I'm going to focus my talk today. Okay, so this is a very basic outline. I have 2 points, okay, that I want to communicate to you all. First is the very basics of wireline receivers. So thankfully, Noman gave a very good high-level overview of the motivation for why we build these transceivers, and also the kind of the very high-level system view. So I'll go maybe one level below and give you a little bit of an idea of how we build the receiver. And from there, I really want to focus maybe on just a few very key topics that maybe will give you some intuition for further reading. Okay, in wireline receivers, there's kind of two really important circuits. The first is the input network, and the second is the CTLE. So I'll try to cover both of them. To be frank, I haven't been able to cover both these topics in 35 minutes, so Ali will cut me off at some point, but hopefully I can at least give you all a little bit of intuition into both of these areas. Okay, so thanks to Noman for his wonderful slide. Actually, let me get the pointer up. Sorry, y'all. Just give me a second. Okay, perfect. Okay, so thanks to Noman for his wonderful diagram. What you see here, this is our kind of general wireline receiver. So Noman covered the transmitter. So what I'll cover now is the receiver, okay? So the transmitter sends us some digital data. This data is transmitted across a channel. As Ali very helpfully pointed out, we can very simply model this channel as a kind of a resistor and a capacitor, so just a very simple wire. If we think of the channel as a very simple wire, we know that there's gonna be some bandwidth limitation because of the RC, right? So this channel will have some low pass filtering. Now, an RC is actually way too simple of a model for the channel, and it's actually much more complicated than that. If you want to dig a little bit more into that, I'll give a reference for a little bit more detail on channels a little bit later, okay? So now that we have the data at our input, we know that the data has been low pass filtered by the channel, so we want to kind of counteract that effect, right? So the first thing that we do in our receiver is we have an equalization, which is basically a high pass filter, which helps to extend the bandwidth of the data that was lost from the channel, okay? So this is kind of the channel response. It's low pass filtered. We have the equalizer, which has a high pass filter shape. So eventually at the output, we actually have a wideband signal again. Okay, so from there, once the equalization has restored the channel bandwidth, we now need to take the analog signal that we have at the output of the equalizer and translate that back to the digital domain. In order to do that, we have a circuit that we call a slicer, and this circuit is just a simple 1-bit ADC. It translates the analog signal into a single-bit digital signal. Okay. Finally, we have this really nice fancy feedback loop. What this feedback loop does is it provides us the clock data from the signal. So this feedback loop actually helps save us a pin because now we don't need to send the clock. The clock is included within the data. So frankly, I could spend the entire talk on just slicers or just clocking. They're both very complex topics with very complex trade-offs, and to do them justice would actually take much longer than just the 35 minutes I have. So today I really want to just focus on the first few stages of the data path, try to give you some good intuition on those first few stages, and then maybe I can leave you with some references so that you can go read a little bit further if you're interested, okay? So the first reference I'll point to, actually, Professor Ali has a whole kind of really wonderful series basically directed directly at undergraduate students called Circuit Intuitions. I would highly recommend you take a look at that. The reference 2 is from that series, and it discusses the basics of channels. From there, if you want to learn a little bit more about equalizers, this high-pass filter that I talked about, I'll cover it a little bit today, but if you want to dig a little bit more into it, you can go to reference 3. Finally, if you want to learn a little bit more about slicers, which is kind of a topic that I would say is very near and dear to my heart as an ADC designer, both references 4 and 5 are excellent readable references on this topic. Okay, so this is our general high-speed wireline receiver block diagram, okay? So this is going maybe a level below what I showed earlier, okay? The key point I want to make here is that all wireline systems, they involve complex trade-offs, okay? So if you need to improve your SNR, that's going to fundamentally mean that you need to burn more power. If you want to increase your data rate, again, that means you're going to need to burn more power. And if you want to increase your data rate, that's also going to hurt you from an SNR perspective, okay? So there's actually all these complex trade-offs that require, let's say, really careful design and thought from like an architectural level all the way down to a circuit design level, okay? So what this means is that you need to be very careful and always choose the right tool for the job. The big advantage that we have in wireline systems is that we have a digital input and we have a digital output. That means that we can make the analog as big or as small as we need to in order to achieve our goals, okay? So this is like a key point. If we look at kind of any modern wireline system, we'll see that actually, excuse me, we'll see that many of these blocks actually can be implemented in either the analog or the digital domain, okay? So the high-pass filtering that I mentioned, the slicer, and even the clock-in data recovery all can be generated in analog or digital domain. So today I'm going to focus just on the blocks that are shared between all, sorry, I'm losing my voice a little bit. The blocks that are shared between all wireline receivers, okay? So first is the input network. The input network provides a reliable interface to the outside world, which in this case, I'm talking about ESD. I'll discuss ESD a little bit more in detail in a second. And the second really important job it performs is wideband impedance matching. Second is the continuous time linear equalizer. This helps us to compensate our low pass channel response. And also, so the key point is that we need to ensure that we have very large high frequency gain from the CTLE in order to ensure that we minimize or maximize the SNR from the rest of the receiver. So each of these blocks inside the receiver that come after the CTLE, these will all generate their own noise. And so having a very large gain at the front end will ensure that we maintain adequate SNR from the rest of the system. Okay, so finally, we have the VGA attenuator. What this does is it allows us to work across a wide variety of channel constraints and ensure that we get a constant swing at the slicer input, regardless of the channel variation. Okay, so first major question that we need to answer when we're building our receiver is how much bandwidth do we need, okay? If we have a given data rate, how much bandwidth do we need in order to support that data rate, okay? So first thing we do is we can normalize everything to the bit period. When I say bit period, I'm talking about the time it takes to transfer 1 bit of data. So in our industry, we refer to this as the unit interval or the UI. And so our frequency of data or F data, this is equal to just 1 over UI, okay? So in this case, I'm normalizing everything to an F data of 1, okay? So we know that if we have a single UI, if we want a repeating cycle of bits of 0, 1, 0, 1, that means that the fastest data period is now 2 UI. So in order to sample the period of 2 UI correctly, we need a 1 UI sampling period. So that means that we basically need to sample every single bit period. This is maybe a little bit intuitive, but actually this is like related to what's called the Nyquist criterion, and ensures that we're always sampling at 2x, we're always sampling at 2x our input frequency, okay? So that tells us how often we need to sample the data, but it doesn't tell us the full story about how wideband our receiver needs to be. So the next thing we can look at is what is the actual spectrum of the data that we're transmitting, okay? So I took just a bunch of random bits at a data rate of 1, as I mentioned, and I put them through an FFT, okay? This is what the FFT looks like. So we can see actually this looks very much like a sync function. We have zeros at every multiple of the data rate, okay? And we can see actually that even at just a single multiple of data rate, there's still a lot of signal energy beyond that, okay? So if we designed our receiver such that we just had a brick wall filter at the data rate like this, right? Actually, we'd be losing a lot of signal information. So in order to counteract that, actually we have to very carefully design our receivers such that the bandwidth goes a little bit beyond the data rate and that we don't lose all this extra signal at the higher rates. The trade-off, of course, as I mentioned, as you increase bandwidth, you're also increasing the amount of noise that you're adding to the signal. So you need to very carefully design your receiver such that you don't lose too much signal, but also that you don't add too much noise either. Okay, so brief interlude. Why ESC? Okay, so probably y'all can see this is a little bit of a silly picture. I was in a bit of a conundrum. I needed to talk about ESC, but I didn't want to worry about copyright violations from taking something from the internet. So what I did is I just figured I can either ask ChatGPT or I can do it myself. And to be frank, I highly doubt ChatGPT could come up with something this good. Okay, so so we all know this story. Okay, we are walking down the street, going to see our friend. We see our friend on the street. We say, "Oh, hey, how's it going?" We go to shake their hands and zap. Right? That's the electrostatic discharge. Okay, that shock that you get, that's actually kilovolts of potential that are generated when the potential that's on your body is discharged to the other person. Okay, the exact same thing can happen to ICs. Now, when it happens to your friend, it's a little shock, no big deal. Everyone moves on. When it happens to an IC, we're talking about kilovolts of potential that can easily damage the IC. Okay, it can completely destroy whatever circuitry is inside of there. Okay, so what the ESC is doing is actually preventing this situation from occurring. It basically ensures that if there's a large change in potential at the input, they'll basically remove all the current, and then there'll be very little current that's sent to the actual device. Okay, that's why we need ESC. If you don't, then it's very easy to actually destroy your parts. Okay. So ESC and U. Okay, this is a very important point for all the people that will hopefully be going to grad school. So I think all of us really, our greatest wish is that all of you will do circuit design PhDs. We all came here on a Sunday, so that we hope to encourage you to do that. And obviously, you're interested enough in this topic that you came on a Sunday to learn about it. Okay, so hopefully, you're at least interested, and one day you'll do a circuit design PhD. Okay, so the key point is, if you're doing a circuit design PhD, maybe the best part of that circuit design PhD is doing the tape out. Okay, so you spend all your time, you spend 6 months to a year designing your chip, you spend 6 months waiting for the chip to come back, you get the chip back, you start building it. You're not wearing your wrist strap, you blow up your chip, okay? It's not fun, okay? Trust me, it's not fun. So key point is, wear your wrist strap when you're building your boards and testing your chips. Soldering, trust me, I spent a lot of time soldering boards in the lab. It's not fun the first time when you do it. It's definitely not fun if you have to solder again because you blew up a chip because you weren't wearing your wrist strap, okay? One other kind of tip that I'll give along these lines, when you're building your boards, make sure to always build 2 boards right away, okay? Because you're going to test that first board, you're going to find some issue, and you're not going to be sure whether the problem is your chip or the board. So if you have 2 boards, at least it gives you a sample size of 2, so you can try to debug a little bit better, okay? So that's just a little tip for y'all if you decide to go into circuit design. Okay, so now we've learned about why we need ESC. So let's talk about the major blocks in the receiver data path, okay? First was the input network, and second is CTLE. Let's see how far I get into this, okay? So here's an example input network. Actually, I really like input networks because they're super simple. They're just resistor, okay? So if you've taken second-year undergrad circuits course, you know enough circuits to get intuition about the circuits I'm about to talk about, okay? So hopefully we can keep it straightforward and learn something new today, okay? So this is our example input network. As I mentioned, we have ESD structures in order to ensure that when you touch the chip, it doesn't blow up. These ESD structures are just PN diodes. And so they have large junction capacitance, okay? So normal ESD can be, way more than even 200 femtofarad, okay? It's just an example. In addition to the ESD capacitance, we also have parasitics from the termination itself, as well as from the CTLE. So these can also easily contribute an additional 200 femtofarad of capacitance. Because we have, the RC, like I mentioned, is actually too simple of a model for the channel. A transmission line is a better model. And if we think about transmission lines, the main thing that we need to make sure of is having matching impedance. If we don't have a matched impedance at the termination, we'll have reflections, and that'll cause issues in our data transmission, okay? So we need very wideband termination to avoid these reflections. Now, here's the kind of key question, right? We have 50 ohm termination. We have 400 femtofarad of capacitance. What is our bandwidth going to be? We can do a very simple 1/2 pi RC calculation. Actually shows that our bandwidth is limited to 8 gigahertz. Now, I think Noman's team is showing a 224 gigabit per second transceiver this week. So how is he showing that if we can only achieve 8 gigahertz bandwidth at the input? It's a very good question, right? So before I answer that question, first I want to talk a little bit about what does this channel limitation actually do to us, okay? So here I have 2 example input networks. One input network has a bandwidth of 1/10 of a UI, and the other one has a bandwidth of 1/100th of a UI. I intentionally chose that because it makes a very simple calculation. In one case, we're going to have 20 dB of loss at our data rate. In the other case, we're going to have 40 dB of loss at our data rate. Okay, the other advantage of this is that actually this is very close to the losses that we'll see in real channels. So if whatever limitations you see from this slide, you'll actually see in real channels as well. And this is actually why we need to build the equalizer in order to overcome some of these limitations. So what happens when we send a bit into our input network? Okay, so first thing is, we know that let me actually tell you what we're putting into the system first, right? So we're putting in a pulse. The pulse width is a single UI. The height is 2 volts, and that's because if we have ideal termination, this is R, so we get a resistive division of 1/2 from this. So we eventually should get a step of 1 volt at the output. Okay, so ideally, what we get at the input is this 2 volt pulse, and at the output, we also want to see a 1 volt pulse. Okay, now we see actually that this pulse does not look very nice anymore. So there's 2 major effects that we have to talk about. Okay, first is the limited bandwidth actually prevents the data from fully settling. Ideally, the data should travel all the way from 0 to 1 and back down to 0 in a single pulse. However, it cannot do that. So it travels up until the time that the data the data changes back to a 0, and then it starts traveling back down. So actually, we lose something like 30% of our signal when we have 10x loss just from the limited settling. Okay. The next effect that we have to talk about is, so that was kind of the amplitude, the amplitude limitation. Now let's talk about the phase limitation or the time domain limitation. Now, ideally, again, a single pulse should be a single UI width, right? Because of the limited bandwidth, now we see that the pulse is no longer a single UI. It actually goes across, let's say, many UI before finally settling out. Okay, so this is what we call intersymbol interference, and this is a non-ideal effect because obviously, ideally, at any given time, the output data should depend only on the current input data. And once we have intersymbol interference, this is no longer the case. So how can we solve this problem? Actually, the answer to basically all problems in life in wireline design is actually inductors. Okay, inductors will solve all of your problems. So let's see what inductors can do for us. So this is a T-coil. Noman also mentioned T-coils because they're also super important in the transmitter side. We use them all over the place whenever we need to bypass a capacitance, okay? So we know that the ESD does not perform any signal processing, okay? It's a very key, important point. The ESD is not doing anything for us besides providing us some protection. What this means is that we can just bypass it completely. And so in order to do that, what we need to do is we need to ensure that we have a short at low frequency and a short at high frequency. Okay, so if we use this passive network, we have 2 inductors connected to this ESD capacitor, and then we have what we call a bypass capacitor around the 2 inductors. Okay, at low frequency, inductors are short, so we have a nice clean bypass through the inductors from pad to the termination. Okay, now let's talk about high frequency. High frequency, the ESD is a short, but because now we have these 2 inductors, those inductors are open, so the impedance looking into the ESD is very high, and the impedance looking into this capacitor at high frequency is very close to 0. So again, we have this nice short from pad to termination. So actually across all frequencies, so you have to be very careful when you design this, but what you can do is anyone can build this. You can build this yourself if you want to. You can look at this reference for, take any RNC value you want. You can take, in my case, I have the 8 gigahertz bandwidth. You can take 10 hertz bandwidth, whatever bandwidth you want. Build this this passive network, and then there's a huge list of design equations that reference 4 gives you. Follow the design equations, set the passive parameters, and you'll see actually that the input impedance is now constant across all frequencies. So it's not just that we've extended the bandwidth to the data rate from 1/10 the data rate to the data rate. No, the bandwidth actually extended to all frequencies. I'm showing to 10x the bandwidth, to 10x the data rate, but if I went to 100, a million, it wouldn't matter actually. So like we had this fundamental problem where we're limited in bandwidth to, let's say, 10x or 10 times less than the data rate, and now we have infinite bandwidth, actually. And all we didn't burn any extra power. All we did was added a passive network, actually. So I really want to kind of stress that passives are amazing, okay? Like, this is kind of an amazing result, right? Like, we have infinite bandwidth now just from a passive network. We didn't burn any extra power, okay? Passive design is everything in wireline, okay? So if you can take anything from this, if you are really interested in doing wireline design, definitely spend a lot of time working on passive networks, okay? So, of course, my model is too ideal, right? I'm assuming there's a lot of, the inductors are much more ideal than they really are. I'm also assuming that there's no additional capacitance on the termination, which we know is definitely not true. As I mentioned before, the termination plus the CTLE can be as much parasitic capacitance as the ESD itself. Now, why is this a problem? So in the ESD case, the ESD is not doing any useful work, so we can just completely bypass it. For the termination, the CTLE, actually, when we charge that capacitor, we're charging a signal processing unit, okay? So if we don't transmit data to that signal processing unit, there's no way that we can get additional processing done. So we can't just simply bypass the capacitor in the case of the ESD. We have to figure out a way to drive that capacitance more efficiently. So the way we do that is, one option is through a shunt inductance, okay? So this used to be our nice little RNC. The C here is just modeling the capacitance of the termination plus the CTLE load. Okay, so instead of having just a resistor for a termination, now I have an inductor in series with a resistor, okay? So if we look at the impedance of just the termination branch, actually we see that there's now a 0 in our impedance. And that's because at high frequency, the inductor turns the circuit into an open circuit. So low frequency, we have the termination resistance. High frequency, we have open circuit, okay? And now, of course, this is in parallel with capacitance. So when we combine this series impedance with the parallel capacitance, we get like this expression, okay? So now we did the algebra, we have a polynomial. Let's try to take that polynomial and relate it back to the physical world, because that's how we build intuition, right? Okay, so first point I want to make is that you can see in the numerator, we have a 0. That's, as I mentioned, this 0 comes from the fact that we have increasing impedance along with the inductance, okay? Now, denominator is second order. That means that at high frequency, we're going to end up with an impedance very close to 0 because the order of the denominator is higher than the numerator. Now, I can say that I knew that that would be the case even before I did all the math here, okay? The reason why I knew that is because we have this impedance, which increases with frequency, in parallel with an impedance that decreases with frequency, okay? We know if two impedances are in parallel, the minimum impedance will always win, okay? So at high frequency, the cap will always win out. Therefore, the numerator cannot be higher order than the denominator. We must always end up converging to 0 for our impedance, because at the end of the day, we have, at high frequency, we have a low impedance in parallel with the high impedance. Okay, so that's kind of some intuition into why this expression comes out the way it does. Okay, so another way to look at this, of course, is that the cap starts to lose impedance at high frequency, and so we can kind of counteract that at least somewhat by adding this shunt inductor, so that we can kind of increase the impedance from this path and get some let's say neutralization of the lost impedance from the cap. Okay. So if we take this equation and then we just say, okay, we want to extend the bandwidth of this just so that the impedance is now still equal to 50 ohms at the 1 over RC, basically the uncompensated bandwidth of our previous circuit. Okay, so if we do that, actually we find that we can set the inductance to this value R squared C over 2, and if we set it to this magical value, actually, and plot the impedance, we can see that the impedance is now 50 ohms out to the original 1 over RC, which was just 1 hertz in my normalized example. So this, of course, implies that now we get some bandwidth extension, but what if we size the inductor even larger? Can we get even more bandwidth extension? Okay, so I sweep just some parameter, which is I show here, but key point is that this parameter means if I make M larger, that means that I have a smaller shunt inductor. Okay, so as I sweep it, actually, I tried to fix this coloring so many times, but it's still messed up. But anyway, so 3.1 here should correspond to the green. So basically, like if we look at as M goes down, that means the inductor increases. So it's this curve here. So we basically see as inductance increases, we see that the bound extension increases up to a certain point, but at some point that extension goes away. So initially we get a bound extension of about, again, 1 hertz being the initial 1 over RC. Now we get a bound extension of about 1.6 with the M of 3.1, and then we can continue increasing the inductor size up till it's 3x the original value, and we'll see that kind of we max out at close to 1.8 bandwidth extension. Now the reason why, as I mentioned before, we kind of have this fundamental limit is because you can size up the inductor as much as you want to. Eventually the cap will always win out. So like at some point, all these curves will eventually converge due to the cap impedance, and that's kind of the best you can do in terms of bandwidth extension. So we can make this inductor arbitrarily large. All that you'll see is that you'll get a bunch of peaking from the inductor at lower frequencies, and at the frequency of interest, you'll see that we converge right back down to the cap impedance. Okay, so now we have a few different curves, right? I'm showing one curve that has a little bit of bandwidth extension, about 1.5, 1.6x, and then I'm showing a couple of different curves that all have almost the exact same bandwidth extension. So how do we choose which topology gives us the actual best performance? And to do that, I think actually looking at the time domain response is the best option. Okay, so time domain response. This is step response, okay? The thing I love about step response is it gives you, in the time domain, it gives you an idea of the DC and the daylight performance, okay? So the step is the infinite frequency, okay? A step always means that you're applying an infinite frequency at the input, and then, of course, the flat is the DC response. So you get both the high frequency and the low frequency response in a single simulation. I think that's quite beautiful, actually. So another kind of key point you can look at is the time that it takes for a step to settle. So in theory, if your circuit is high enough bandwidth, it should be able to completely settle a step input within a single UI. Okay, so that's kind of the key metric that we use when we're kind of evaluating these SerDes. How long does it take in order to get to the final value that we're looking for? Okay, so again, I applied a 2-volt step at the input. This implies that we should get 1 volt at the output, and we just want to see, okay, as I size up the inductor, which one's going to give me the best settling response? Okay. So a few kind of things that we can gather from this step response, right? First thing is that as we increase the inductor, the rise time always improves. You see that the largest inductor actually gives us the best rise time in terms of like approaching the final value first. And then it kind of decreases as time goes on. And this dashed line, which is the uncompensated response, this has the worst rise time. So let me try to give some insight into why increasing the inductor size improves our rise time. Okay, so the rise time of this circuit is going to be just set by the amount of current that's going into the capacitor. So the more current that you have going into the capacitor, the faster the rise time. Now the current into the capacitor is set by the current from the source, which is kind of fixed. Let's say it's fixed, right? The current from the source, which then gets split into the termination and the capacitance. So as long as we can minimize the current through the termination and maximize the current through the capacitance, we should maximize the rise time. Now, of course, we know that the inductors oppose the change in current. So for any given time, if we have a certain voltage on the output, the change in current will always be reduced as we increase the inductor. Okay, so this means that anytime we always if increasing the inductor always will minimize the amount of current that's going through this path. Okay, so that's why we get this improvement in rise time. Now there's some clear trade-off here, which is the overshoot, right? You can see that actually as we increase the inductor size, we'll actually get a pretty significant amount of overshoot in the signal, actually up to like 25% overshoot. This matters because we don't actually care about the rise time, we care about actual settling time. And the reason why that inductor increases the overshoot is because, again, it opposes changes in current. So there's going to be kind of, when we apply a step, there's going to be 2 major regimes where we have changes in current, right? Initially, we get a big step, and that's going to rush a lot of current into the capacitor, and the inductor will try to fight any current going into the inductance. Now, as we get closer to the final value, the slope of the current will change because the capacitor is being charged more slowly, and more current is trying to go into the resistor. The inductor won't like that change in current, and it'll try to force more current back into the capacitor, which actually causes this overshoot. So the larger the inductor, the more it'll fight the current change in the capacitor and cause the capacitor to basically shoot above its target a little bit. Okay, so let's zoom in a little bit closer. Obviously, you can't get too much of an idea of what the final settle behavior is from this far out. So I've zoomed in a little bit closer. Now we can see the error bands of our signal, because we really don't care about which one gets the final value first. We care about which one settles, like I said before. So in this case, of course, what does settling mean, right? Settling means that we have to define some amount of error that we find acceptable. This will, of course, be set by the application that you're designing for, and so this will change a lot depending upon the system that you're designing. But in this case, I just arbitrarily chose a value of 2% for my threshold. And so if we look at 2%, actually we can see that all the signals besides the smallest inductor I showed, all of these settle much slower than the uncompensated case. Actually, you can see that with overshoot, all these signals come in much later than this value. Okay, the only one that doesn't is this the smallest inductor with the smallest overshoot. Okay, now one key point I want to make here is that I set 2% as the threshold. What if I had set 3%? Okay, if I had set 3%, that means this line would be here, and actually the case with the smallest inductor would be almost 2x faster than the uncompensated case. So you can see that the best circuit for the job depends a lot upon our requirements. And so we have to think a lot about the right specs for our circuit before we go and design them, because that'll determine a lot about what the optimum topology is, okay? So major point I want to make here, actually the inductor, the design with the smallest inductor, this also had the smallest bandwidth extension. So that means that the design with the smallest bandwidth actually gave us the best overall performance. It's a little bit counterintuitive. We always think best bandwidth will give us best settling time, but actually that's not the case when we start thinking about more complicated circuits with inductors, right? So this key lesson I want to point out here is AC bandwidth is not everything, okay? Time domain response is the only time you're actually simulating your circuit. So whenever you do an AC simulation, the simulator is actually taking your circuit, it's making a model of your circuit, and it's telling you what the response of that model is, okay? So you hope that that circuit is modeling your actual circuit behavior well, but to be honest with you, you really don't have any idea, okay? When you actually apply a step response to your circuit and see how it behaves, that's the only time that you're really identifying any problems within your circuit, okay? The best engineers I know, they always look at transient waveforms, okay? So if you want to like read further on this subject of like wideband circuit design from a time domain perspective, actually, I think this reference 7 is a really good reference. But just one more thing, I only showed the magnitude response in AC land, right? And of course, like we know that that's only half the information that we get from AC. So let's go back and let's see if we forgot something back in AC land. Okay, so now, okay, like I said, we only showed magnitude before, so let's also show phase as well. Okay, so this is the phase response for the different circuits that I showed earlier. Now we can see that the case with the largest inductor actually has, I would say, the sharpest phase change. Okay, and so whenever we're talking about the sharpness or the amount of change in something in a certain quantity, of course we're thinking about the derivative. Okay, so if we take the derivative of the phase, we get the curve on the right, and actually this is quite an important metric within our field. It's important enough that we gave it a name. It's called group delay, and it's just like I said, the change in phase with the change in frequency. Okay, so we can see actually that the case that gave us the best settling response was also the case with the minimum group delay variation. You can see that this green case is the case with the minimum inductor size, and the group delay stays very close to -20. Okay, in all of the cases we see huge group delay variation, and those also tend to give us largest overshoot and the worst kind of time domain response. So I won't go into too much more into depth in this, but I think this is probably something to think about in the future if you're designing these circuits. Okay. Actually, I only have a minute left, so I'm going to skip the topic of CTLE, but I do actually, let me just get to my summary, actually. I'll skip all this stuff, okay? If y'all want to read a little bit more about CTLE, it's in the slides. If you want to get my perspective on it, I'm more than happy to give you a whole diatribe about it after this talk, okay? I'm more than happy to talk to any of y'all. But let me just kind of give a brief summary, okay? Wireline is a super broad field. I actually only talked about the most basic fundamental circuit in wireline, which is just a resistor, okay? I spent half the talk on a resistor, okay? So that's how interesting and broad our field is, okay? There's lots of interesting constraints and lots of opportunity for learning. In general, the early stages in the data path, they have generally the biggest impact on system performance, and that's kind of why I chose to focus on them for this talk. big picture idea, passives are everything when it comes to maximizing the bandwidth without consuming extra power. And so any really good receiver design or any really good high bandwidth wireline design will have very carefully designed passives. Finally, I'll skip the point about high Q because I didn't talk about high Q too much, but time domain simulation is as real world as you get until your chip hits the lab, okay? And you'd much rather find issues in one domain than the other, okay? Definitely want to find the issues before the chip hits the lab, okay? So, yeah, if you're anything you're designing, you should be doing step response. You should be looking at the step response of that circuit, and you should make sure that you understand everything that happens within it. And I think that you'll get a lot of insight from that process and become a much better designer as a result of it. Thank you very much for your time.